Howdy and welcome back. We're going to continue our discussion on copy semantics by introducing some new terminology. The first is going to be shallow copy, which we briefly alluded to in the previous video, essentially constitutes a member-wise copy of the data members of one object into the corresponding fields or data members of another object. We'll then get into this idea of a deep copy and go ahead and discuss how it can be used to help resolve some of the issues, if you will, that we've been observing with our vector int. So first, let's go ahead and define more properly what a shallow copy is. So in C++, the default copy mechanism, when we are initializing a user-defined type with an object of the same type, or assigning to an object of user-defined type an object of the same type, is going to be what's known as a shallow copy. All a shallow copy effectively means is that the object is going to be copied exactly as is during the initialization or assignment process. So each data member is going to be effectively copied exactly as it presents to the corresponding member data location in the other object. So what this means for, say, two objects of our vector int type, v1 and v2. If v2 was being initialized with v1, or if v2 was being assigned with v1, the capacity field, let me, I guess, use the same video or the same, colors as the previous video. The capacity field would be copied as is, which would mean that this integer value of 2 would be placed into the corresponding field of v2. So v2's capacity, also 2. Furthermore, size, the value stored in v1 size would be copied over precisely as it presents in v1 into the corresponding size field of v2. Now, finally, where the shallow copy is going to really present the motivation for a deep copy is when we're copying the value of array into the corresponding field of v2's array. In this case, notice that we have an address to an object residing on the free store. And when we copy that address into the corresponding field of v2, essentially v1 and v2 are going to be storing the same address within their array pointer. The consequence of this is going to be that both v1 and v2 are going to be pointing to the same free store object. In other words, this dynamically allocated object is going to be shared between v1 and v2. And when you think about this, this probably wasn't what we would have liked to happen. And we'll get into very shortly how a deep copy can resolve this shared dynamic memory. But let's talk about some of the limitations of a shallow copy to begin with, or a member-wise copy, if you will. In a lot of application, a member-wise copy will be completely sufficient. However, when we're dealing with objects that have pointers inside of them to dynamically allocated objects, a shallow copy of that object might not be sufficient. And here's the reason why. Only the values from the pointers are copied into the other object's corresponding pointers, but not the dynamic data that is being pointed to. In other words, v1 and v2 end up sharing an array opposed to v2 having its own array with the same values as v1's array. This consequence of simply copying the address over into the corresponding field, again, we're looking right here at uArray, and we're saying, okay, well, I copied this address into the corresponding field in v2. This, as we pointed out in the previous slide, is going to result in the dynamic data being shared between the two objects. And again, this dynamically allocated array is now being pointed to by v1's array and v2's array. And again, this probably isn't desired behavior. So how can a deep copy help us resolve this? Well, in a deep copy, the objects pointed to in one object are going to be copied first. Then the other object's corresponding pointers are going to be assigned the address of the copied object. So that might not be clear, but the idea here is going to be that in that case where we just described a V1 being used to initialize, say, V2 with, we would create V2 in a manner that it would have its own dynamically allocated array, and the values of V1's dynamically allocated array would be copied into the corresponding indexes of V2's dynamically allocated array. And at the end of this procedure of a deep copy, V1 and V2 would look identical to one another, with the only difference being that V1 would have its own array, which would have the same values as V2's array, but they'd both have their own dynamically allocated array. There would be none of this sharing. So after a deep copy has been completed, each identifier will have the same values for the dynamically allocated object, but stored in distinct objects that each of them is the rightful owner to. So let's go ahead and see what this looks like on initialization. So let's say vector int v1 is going to start out with single integer value within its dynamically allocated array, initialized to 0. We'll push back the integer value of 1. What's not shown here is the resizing that would have to happen, but effectively at the end of the pushback operation, v1 is going to be composed as follows. It will have an address to a dynamically allocated array. It will have some sort of size. In this instance, that size is going to be 2. I don't know what I'm doing with the colors. So let's just say the size is going to be 2 and the capacity is going to be 2 as well. Excuse me, we did not do any sort of resizing operation here because V1 would have been initialized with an array, which is 2 times the initial size, which in this case, capacity of 2. So irrespective, just here's V1 all set up. Here's its array out there in memory. Now in a deep copy, let's say we initialize V2 with V1. The end result's going to look like this. Notice here that, and I guess I missed an update here. Sorry about this. This is actually V2. Hold on, let me make this look a little better. Okay, we have V2 here now, correctly shown as such. And notice that the capacity was copied over from V1's capacity. The size was copied over from V1 size. However, we'll observe our difference here. The address stored to in the array field of V1 will be different from that of V2 because we're performing a deep copy. So V2 here's, I'll do this in, I guess, purple. V2's array is going to have a value that's different from that of V1. And I guess just to be consistent with all these colors, if y'all haven't figured out yet, I like colors. Is that V1's address is different. However, if we look at the composition of the array pointed to by V1 and compare that to the array pointed by V2, notice that the values at the corresponding indexes were copied from V1's array into V2's array. So at the end of this deep copy mechanism, V2 and V1 look identical to one another. The only difference from the shallow copy here is that both V1 and V2 own their own dynamically allocated array. They're not shared. And the same effect of a deep copy on assignment can be defined similarly. So we could have, say, the capacity field being copied over into V2's capacity field when V2 is assigned with V1. The size field can be copied directly over. However, we have dynamically allocated memory, so we're not going to directly copy over that array. Instead, during the assignment process, we're going to have V2 go out and get its own array. And this is reflected in the difference in the addresses between V1's array compared to V2's array. However, notice that the composition of these arrays is identical. V2's array at the 0th position has 0, just like V1's. V1's position, or index of 1, its value would be copied into the corresponding position in V2's array. And we have this silly issue again, where this should have really read V2. So again, the consequence here is at the end of this assignment operation of assigning V2, V1, we can see here that the composition of these two objects is more or less identical. They look the same. They have the same capacity. They have the same size, which one would expect at this point if we're saying V2 is equal to V1. For instance, if we had two integer objects, int I is equal to 8, int j is equal to 9, if we say j is equal to I, at the end of this statement, we'd expect j to have the value of 8. Just like what we're observing here, V2 looks identical to V1. However, each of these two objects, V2 and V1, is going to have its own dynamically allocated array. However, the values in V1's array and V2's array are going to be identical directly after this line. And any changes made to either V1 or V2's array thereafter would be only reflected in the object whose array was modified. So with all this in mind, I think we're kind of seeing now that, okay, well, hopefully you're seeing at least that a shallow copy is going to be insufficient when our user-defined types own some sort of resource, in this case, a dynamically allocated object residing on the free store. So the next question is, okay, well, you kind of showed us what a deep copy is. How the heck do we go about implementing a deep copy policy for our user-defined types? And that's what the next video will get into here.